Hi, welcome to not Freak Out, College Algebra, sorry. Three, four zeros of functions. So it does a little bit of stuff we talked about in 3.3. Well, fundamental theorem of algebra is the first thing. Fundamental theorem says a polynomial of degree n has n complex zeros. Complex just means they're real and or imaginary. So n tells us the number of answers we should end up with. Nice thing about real zeros is they could be counted twice. For example, multiplicity of 2, but they will always show up on the x-intercept. So if I have a polynomial of, degree 4, dot, 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 but I only see something like this, I know that I have this answer has a multiplicity that's even. So, for example, multiplicity of 2. So if that's true, let's assume this is true, then I have two real solutions, but I have a degree of 4. So I know that I have to have two imaginary as well. Now, the nice thing about imaginary zeros, they will always, always, always come in pairs or conjugate pairs. What I mean by that is if 4 plus 3i is a 0, then 4 minus 3i is 0. They also do not show up on graphs. So if I get a simple polynomial like this is just, an x squared plus dot, 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 dot. I can see that I don't have any real zeros. So both my answers have to be imaginary. I recall that if x equals k, then x minus k is the factor. So x equals 3, I can remember that x minus 3 would be the parenthetical. Same thing with imaginary, as it turns out. X minus 2i in this case would be something. And where this one you'd have x minus 3 minus 4i in parentheses. So you'd get x minus 3 plus 4i. And by extension, you would also know that 3 plus 4i is also a parenthetical. So you would also get 3 minus 4i in there as well. What are the zeros? In this case, we can set them all equal to 0 and solve. So I'd get 3 with a multiplicity of 2. And of course, we would get x minus I equals 0. So x equals I, and x equals negative 1i. So I would have 3 with a multiplicity of 2 and positive and negative I with a degree of 4, giving me 2 real and 2 imaginary zeros. Okay, four-step process. First, again, I would look for real zeros that are on there. So in this case, I'm going to use x equals negative 1. And if I need to, I can also use 1, 2, 3, 4, x equals 4. Okay, so I'm going to plug negative 1 and synthetically divide. So 1, negative 3, negative 6, 6, and 8. Negative 1, negative 4, 4, 2, negative 2. Uh-oh. Did I mess up somewhere? 1, negative 4, positive 4. Oh, this would be negative 2. That just positive 2, so 8, negative 8, and 0. So here, we obviously have x cubed minus 4x squared minus 2x plus 8. So I'm going to synthetically divide again with 4 if you wanted to. X cubed minus 4x squared minus 2x plus 8. You could factor by grouping. So take out an x squared, x minus 4, take out a negative 2, x minus 4. We're going to get x squared minus 2 and x minus 4. Well, since I'm synthetically dividing with x minus 4, I should end up with x squared minus 2. Let's take a look. That's exactly what we end up with, x squared minus 2. Don't forget our x minus 4 as well as our x plus 1. So we're going to get the answers of 4, negative 1. And with here, we would get plus and minus the square root of 2, giving me 4 total solutions for my 4 degree. All of them just happen to be real on this one. Sometimes it's hard to find the zeros on the graph, so we actually have an app on our calculator that can do that for us as well. We go to apps and we'll go to Polysmith. For me, it's number 9, Polys 1.2. And I'm going to pick polynomial root finder. In this case, you would just plug it in. So for this case, order means degree. So in this case, I'd say order 4. And then these buttons on the screen are correlated to the gray buttons below. So normally your screen would be right on top of this. So in this case, if I want to press the help, I'd press trace. If I want to go to the main menu, I'd press Y equals. I want to move forward and hit next. So I'm going to hit the graph button. And here I would just type in my coefficients. So in this case, 1, -3, -6, 6, and 8. And I'm going to hit solve. And it tells me some solutions. So if I flip back a slide, we note that our answers were 4, -1, and plus and minus √2. Well, here I get 4, -1, and -1.414, as well as positive 1.414. Well, what's the second? Oh, what's the square root of 2? 1.414. So it makes perfect sense. We get the exact same answers. So that's all about the Smith app right there. Okay, let's see. We can obviously graph it, and we see that again we get this bouncing. So I can use it twice because that's got that multiplicity feature. So I'm going to synthetically divide with -2. 1, -4, -13, 28, and 60. 1, -2. My pen's not working anymore. That's kind of frustrating. All right, let's see. -6, 12, -1. Oh, goodness gracious. I'm just going to erase all this. I think my pen not working and my handwriting being bad have combined into 2 big mistakes. So let's take a look again. 1, -4, -13, 28, and 60. Drop the 1. -2 is -6, positive 12, 1, -2. What the heck? Why is that happening? Ah, -13 plus 12 is obviously -1, so this should be +2, therefore 30, therefore -60 will works out. Again, I can use -2, so I'm going to, again, with these numbers, -2, 1, -6, -1, 30, 1, -2, -8, +16. Oh, goodness. 15, -30, 0. So we get x squared minus 8x plus 15 and x plus 2 quantity squared. I can factor what multiplies 15 adds -8. That'd be -3 and -5. So we would get 2, -2 with a multiplicity of 2, +3, and +5, just by setting all those parentheticals equal to 0. Okay. What about imaginary zeros? Well, I can graph it, and I can usually find that, in this case, -1 would show up on my graph. So I end up with x squared plus 9 and x plus 1. And I could solve this. Normally I would try to factor. Unfortunately, it doesn't factor. So I can actually just set x squared plus 9 equal to 0. And I had -9, so I get x squared equals -9. Square root, square root. We are square rooting a negative. So that's why we're going to get plus and minus, in this case 3i. In fact, this is kind of the core reason that imaginaries always show up in pairs. How do you create an imaginary number? Well, you square root a negative. But what happens when we square root? You get plus and minus. So by its very nature, square rooting generates two answers. That's why imaginaries work together there. Linear factorization. So if I know my answers are x equals -1, x equals 3i, and x equals -3i, all I'm looking for is the parenthetical equivalent. So that would be the linear factorization because they're all turned into linear quantities. This, by its very nature, is not linear, so it wouldn't qualify. So that's what we did on day 1. So day 2 of 3.4 is sort of going that way. Now, if I know that 8i is an answer, I have to know that -8i is an answer because the conjugate always comes with. Now, I don't know the leading coefficient, so for the sake of argument, I'm just going to call it a. But it wants it in linear factored form, so I just want to do x minus 2, x minus 8i, and x plus 8i with an a out front. This next one, find a polynomial of degree 3 with zeros 1 and 3i, and f of 0 equals 18. Well, if it has a degree of 3, I know I need to have 3 zeros. It only gave me 2, but because I have 3i, I should remember that I automatically get its conjugate of -3i. So my parentheses are going to be x minus 1, x minus 3i, and x plus 3i. I don't know my leading coefficient yet, so I'm going to put it as a. I'm going to put this f of x out here, or y. Either is perfectly fine. Now, I know that f of x equals 18, so I'm going to plug in an 18 for f of x. But what does this 0 mean? Well, that's the x value. So I'm going to put a 0 in for every single x value, which means all I need to do is solve for a to sort of get an understanding of what's going on. So I get 18 equals a, 0 minus 1, 0 minus 3i, 0 plus 3i. And simplify, so -1, -3i, positive 3i, and all 4 of these things are being multiplied. So -3i times 3i would be -9i squared, times -1 gives me 9i squared a. Quick remember, I squared equals -1. So we get 18 equals 9 times -1 times a, so -9a equals 18, so therefore a has to equal -2. Which means, in factored form, this would be -2 x, I forgot the numbers already, minus 1, x minus 3i, and x plus 3i. That would be factored form. However, I scroll down a little bit, it wants it in standard form, which means I have to multiply it out. I have to multiply this out to get it into standard form. So I get -2 times x minus 1, x minus 3i, x plus 3i. Technically speaking, because order doesn't matter in multiplication, I can multiply any 2 parentheticals together first. I'm telling you that if you're multiplying conjugates, whether that be radicals or imaginaries, you should multiply those 2 parentheses together first because they're going to simplify. So x times x, x squared, plus 3xi, minus 3xi, minus 9i squared. My middle terms cancel out. My I squared turns into a -1, so I get x squared plus 9. And I can multiply it out again. X times x squared, x cubed, 9x, x squared, 9, And I can distribute -2 to all that stuff and put it in standard form where it go highest degree to lowest. So -2x cubed minus 2x squared minus 18x minus 18. I just flipped the order of these two for that standard form of exponents. Thank you for listening, and I hope you have a great day.